Ok, buenos días. Voy a dar una pequeña presentación en inglés. So, good morning, everyone. I'm here. It's my pleasure today to introduce my colleague from the University of Sassari, Luca Cardello. Luca is a field geologist, most of all, and a structural geologist. With a long-standing career, he finished his PhD at the University Roma La Sapienza, and then he finished his master degree at La Sapienza, and then he did his PhD at the ETH in Zurich. After that, a long journey between university in France, in Switzerland, and in Italy. In detail, Orleans, then Ginebra, then Roma La Sapienza, and now he landed at the end at the University of Sassari, where he is a tenure track since 2020, isn't it? Okay, 2020.
He's studying.
Yeah, I did. So Luca is also the responsible for the geology of this project that is an international project called the Einstein Telescope. The Einstein Telescope is a project to choose a site in Europe where to build this big telescope. So it's, I think, 4 or 5 years that they are doing geological studies in Sardinia, because our candidate, and this is support also by Spain, I discovered, is Sardinia. So the talk of Luca will be mainly on that today, on the implication of geological study for big scientific projects such as the Einstein Telescope. So I don't say more. I said enough. I let you to speak. Thank you, Luca, and good talk.
Muchas gracias a todos para estar aquí. Lo siento por mi español, entonces voy a hablar en inglés. Also because the vocabulary is more complete in English. So, e non parlo il català. Sorry. So, Andrea said much of the beginning of the presentation. So, thank you very much to invite me here. And I'm very happy to show a part of our results about the candidature of Italy, the Einstein Telescope. So, so just say where I was, and so we can skip it. The only thing that I want to add is what is my playground, so the places where I've been, the places where I've been working to. It's mostly in the Mediterranean chains, and lately I've been focusing on Sardinia. Muy bien, aceptar. Flash. Entonces. Perfetto.
Adesso questo documento.
Com'è che si fa per... Ah no, proprio così, lo sapevo che dovevo usare Mac io. That's the problem between Mac and the others. But anyway, so let's see if it works. So let's skip this part. It was mostly what I do. I can tell you straight away. I've been working on carbonates for most of my career, but recently I've been more and more into crystalline basement, because this is the area where the Einstein Telescope, and we are going into detail onto that in a while. So those are the keywords that I've seen are very much used also in your publications, or at least some of you in this group. Is when we talk about structural inheritance. So it means the memory that the crust has of previous tectonic phases, and sometimes this memory brings to reactivations. And this is also part of the agenda of today. So first, we start seeing what's the Einstein Telescope, which also involves Spain in support of the candidature of Sardinia to host this telescope, then Y Sardinia, and then we will see some applications also in terms of de-risking, so knowing the risk of an area and eventually lowering it to assess the risk related to this eventual construction of the telescope. So in first approximation, this is the commonly used sketch of what the Einstein telescope would be. It's a super large structure. We are talking about three different I won't use it. Three different laboratories that will be connected by three tunnels. And as you can see, they are as far as more than 10 kilometers away from each other. They are underground. Of course, this is ideal without topography. And actually, we do have topography in Sardinia. And these laboratories to detect gravitational waves need to be shielded by 120 meters, 150 meters of rocks on top of the laboratory. And those are towers that are tens of meters high. So it's a very, very large area that needs to be very, very quiet. So it doesn't need to have ambient noise, which is too high. And there are very few candidate sites in Europe to have these characteristics. So for us, for the geologists, what is important is that there is a good rock volume, good mechanical properties. So we should avoid any water circulation. So most likely no faults, no active tectonics. So what I did in these years was to see the interplay between tectonics, volcanism, and we have done a lot of dating and geochronological support to frame the evolution of this area. So we are not the only ones. When it's a competition, it means that there is other candidates. The other candidates are, so you see the position of our common candidate, Italy, Spain, and Croatia for the moment are supporting these sites. Then the Belgian and Netherlands government support the construction of another site in Belgium, very close to Maastricht. And then the German site is not very far from Prague, but still in Eastern Germany. And you see, I plot them on the acceleration map. So in other words, it's the seismic risk map of Europe. And you see our countries maybe couldn't candidate a better option than this, also because it's one of the lowest populated areas. So it has very little anthropic noise and very little also seismic noise. So the other candidate sites, for example, the one, see, this is the southern tip of the Netherlands. The other candidate site in the Belgian Netherlands is actually in a very seismically active zone related to the Rhine-Graben situation. So not very good for our friends. In our case, in Sardinia, we have very, very little seismicity, very few earthquakes recorded by the national network. And you see most of them are just in the northwest, so are related to the Tyrrhenian Sea opening and collapse of the margin up there in Olbia. But for the rest, the sparks you see here is mostly related to mining. So these are explosions, it's dynamite. So not through earthquakes. Those are very, very little. And anyway, we never reach the levels of the Rhine-Graben. And we see the expected magnitude, even in the most seismic part, which is anyway out of the island, is around 2.5 Richter magnitude. And with regards to the noise, the physicists, in collaboration with different countries, try to establish what's the ambient noise in at least these two major candidates. the Belgian Netherlands, and Sardinia, and you see that the frequencies are very low, which are the ones needed for detection of gravitational waves. So we're talking about between 1 and 10 hertz, and the seismic noise and the natural, the ambient noise of the Italian candidate sites are lower than the one from the Belgian Netherlands. And this is also true when we compare, you see, 110 again. And in this case, Italy is green, Belgium, Netherlands is black, and Germany is yellow. They are more noisy than what we are. So in this case, it's very good, and this is a very strong argument for this. And the reason why is that Sardinia is far away from any plate boundaries, and also it's pretty stable. Recently, we have also published about the use of the information from Copernicus, you might have heard of, and you see there is no color difference. So this means that there is no blocks moving even within the Sardinian island. And this is the area that we are going to candidate. So it's pretty stable, at least from what we can see from the satellite. And it has been chosen this area for two reasons. One is that it's far away from major inherited faults, which are those that cross-cut the image Jurassic limestone seen here. Those are the granites, these are schists, more or less, and other metamorphic rocks. Pegmatites in here, there is a small fault, but it has been it's much older than the granites, so it's not a problem. And anyway, this is the area that has been chosen far away from any potential candidates for noise. Well, this is a detail that we adapted with fieldwork, and you can see again this is the triangle, but actually, as you can see, there is also other configurations that are under study, because probably this configuration with longer arms that reach 15 kilometers length are maybe working even better. So there was it's 5 years that we were working on it, and in the last year we have been also adding more data also from a private company that did the drilling and some geophysics in the area. So I say that our laboratories need to be 150, 125 meters at least shielded by rocks, and this is the tunnels, you see? The depth of the tunnels. When you are below, for example, the plateau, you need to dig for 700 meters. No way that we can know exactly what's under there. Okay, we are a crystalline basement, and the previous wells we did reach just a little part of it. That's why this is colored and the lower part is not colored. So the challenge here is knowing the geology also down here and trying to make the best of the surface to model the best the depth. So we went through preliminary drillings, geophysics of the area, so geoelectrics and seismic, active seismics. And then we have done all of these boreholes, and the very nice discovery, this is from the last months, is that actually what is to the surface may be somewhat extrapolated down to depth. We couldn't know at the beginning if there was a pattern down there, for example, the granites. But for example, I'm talking about the metamorphic rocks. We didn't know if we would define some other rocks. But besides little variations that you can find inside, well, then you have the same lithologies all the way down, and it's very good rocks with very good mechanical properties. In this case, from the west point in here, we found this beautiful granular. It's very good for the purposes of this construction. And in here, for example, we are in the middle of the north-south arm of this L configuration, where it intersects the previous triangular shape of this configuration. And we see that actually we do have intersected also other methodologies like volcanic rocks from the Permian time, and we're trying to understand more about the temperatures and other chronological constraints on this area. But besides knowing what's depth, we need to know well what's the surface. So we did a geomorphic and morphostructural study, and we have seen that the faults actually, the few faults there are limited to say 1.5 kilometers. No, not very dangerous for this type of engineering of deep tunnel digging. Most of these structures are east-west. This is an important datum to retain. And we see that these east-west faults sometimes occur parallel either to dikes, basic dikes, or to acidic dikes, which is very important because it gives us also an idea of what is the structural inheritance of these structures that had a volcanic tectonic function during the emplacement of these mafic and acidic dikes. And also we do see there is a cross-cutting relationship between different structures with different orientations. Usually north-south structures, so aligned as the island is, north-south, are younger than the other structures. So those are the old ones. You see, for example, here there is a detail of the granitoid intruding into the schist in the central part of the candidate area. And this is an east-west structure. As this is the limit of the batholith going inside through these, using these faults to make these steps. So this means that also the emplacement of batholiths was guided by these east-west faults. This is the structure inheritance. And we do see here these dikes, and they are also north-south. So it's like a chocolate table structure within the crystalline basement and within faults that were dated as well. Those faults were reactivated later. We come that to in a moment. But to make all the constraints, and here also there is the help of Andrea, we are doing, that's why there is the star is for Andrea. You see, we do also some Raman spectroscopy to know better about the maximum temperature of these metamorphic rocks. We have been dating in Rennes, so in France, the zircons, and use the same minerals to know better what was the cooling part of these rocks. So we have been using different techniques. We've chosen a few of them just to try to constrain from higher temperature, older stuff, to lower temperature, younger events, geological events. So this is important for the de-risking because of course we are more interested in what happened in recent times because the Einstein Telescope won't be built in the Jurassic. It will be built in the future, so close to us, so in colder conditions. But we need to constrain the whole geology. Okay? And this is one of the least known areas of Italy. So in previous years, there was some apatite fission tracks dating. This is very important for knowing the last 100 degrees evolution of these rocks. And well, as you see, the data are scattered from the Jurassic period to recent times. So this means that there are very peculiar situations, and we have been trying to see what's the meaning of that also in our area by adding a few more data. Of course, we were more in the north in the beginning because this was the most tricky area. And the mine, I told you, Sostenatus mine, this is the one that gives the name to the project, is more into the south, but we have added also some more samples later. This is the situation. So you see there is a rough topography with plateaus at 1,000 meters. We have some boreholes, and then there is valleys as deep as 800 meters. So there is some vertical gradient, and we have been sampling in collaboration with a colleague who is now in England, Chiara and Amadori, and we have been collecting a bit of all the lithologies in the area to know better the exhumation path, but also we have used this same zircons also for knowing the magmatic age of the original magmatic age, for example, minerals contained into the metamorphic rocks. See, they are very, very old. Maybe they sound familiar for those of you who work in the crystalline basement. Also, because it's in common with what you have here in the Cambrian or Variscan schists of Catalonia. And we have been able also to date some very large intrusions that were never dated before. And you see they are a bit older than what's known so far. So this is the new age that we provided, and it's a bit older than what's the average age. And well, I moved a bit forward. The most important thing is the most recent part, and we have seen that these are two techniques that allow to date the cooling of these rocks. We do have them in the somewhere in the Cretaceous and then in the Paleogene. So we can know the exhumation through these temperatures. So 880 degrees for Cretaceous, so which corresponds roughly to 6 kilometers, and 100 degrees roughly corresponding with the present day geothermal gradient to 3 kilometers reached already in the Paleocene. So if that was more or less the situation, this is typical of very slow exhuming rocks. So this means typical of a not tectonically active region. Okay. Those are the constraints that we could provide, which somewhat confirm what we knew in other areas, but now we know it also within the candidate area. This is the path, so the constraints of Andrea are here. Of course, we miss a part of the story here, but doesn't matter much because the other constraints comes from these areas in blue in here. So you see, limit between Jurassic and Cretaceous 6 kilometers depth or less, and then during the Cretaceous 3 kilometers depth. This is the erosion. This means that it was uplifting at that time until when in the late Cretaceous it reached colder temperatures, then again was heated again, and then since the Eocene it's pretty stable. See, this is one sample, but it tells much of the story of the area. I just chose this one to simplify this situation. So then the question is, there was any reactivation maybe related to the Pyrenees, so in the colder part of the story. So another thing was that, just to resume what I say, that the faults that we do have are more or less parallel, most of them, to the dikes of the area. You see, east-west again. And also, we have been trying to date these faults with the fault gap. We sent them to Australia. We dated a few of them. And guess what? The story is Jurassic Cretaceous, exactly as the most of the exhumation of the area. So Jurassic Cretaceous, we use this dating technique of light. Maybe you're familiar with that. It's basically the clay that you produce them in the faults. Usually you have a very tiny sliver. It's very easy to dig. And when it's fresh, you can date it. And the finest fraction is the one that is usually the less critical. So you can use that as a proxy to say when was tectonically active for the last time. You see, nothing younger than the earliest Cretaceous. And then our question was, is it possible maybe to see these faults as a thin sedimentary faults within the carbonate cover? So we moved a little bit to the east, and before going to have a bath in the city, we have seen this mountain, which is Carbonic made, Jurassic to Cretaceous, and we see that faults stop in the Cretaceous. This displacement is very little with respect to with this displacement you do see here. Okay, here there is more than 300 meters of offset, and then is sealed more or less by these Cretaceous faults. So it's kind of a post-faulting stratum that you see in here. So yes, this is another east-west fault, as you can see from the map, more or less. See, east-west fault, and again, it shows a Jurassic, a late Jurassic, early Cretaceous story. We are here. So this is the fault gouge ages, and you see it corresponds roughly with something that has been detected by previous workers. This is Costamagno, who died months ago, and you see there is not much known about this period. I know there is also some ages from the Pyrenees about this timing, and it would be very interesting to compare also with your structures to fill this gap. And that was the idea of reusing these ancient inherited Paleozoic faults as post-breakup dismantling of the margin of southern Europe. You see the position of Sardinia. It may be placed maybe closer to Iberia, maybe farther, depends on the geographical map, the paleogeographic mapping in use. But the idea was that there was some reactivation of these faults at that time. So, is it just a local thing, or can we extrapolate and knowing more, going more to the west? So we have been sampling also in the covering units. We are in the western part of the island, and you see here they speak Cardello in Alghero, and we've been sampling a different type of rocks, trying to cover the deformation of the area. And in this case, we have used maybe two samples. Yes, two samples for the potassium argon on plate gouge on these two faults, the fasten here and the north-south normal fault in here, trying to see what's the age. For the rest, was tried with the uranium lead, like you do in this department, and we try to see if these faults that seem to cut just a little bit across the Cretaceous could be dated. And well, this is a very nice story where you have a shear zone that we try to date with the potassium argon. I guess more or less same age like we had in the Einstein Telescope zone, which is just 100 kilometers away, or to the east. And here we got very similar ages. And then with uranium lead bingo, we found neogen deformation. So this means that these structures are reused again once Sardinia shifts away from Iberia and stands alone in the middle of the Mediterranean Sea. Still moving. Those are the preliminary data that we are doing in collaboration with Variscan, with Thomas Blaise. And so this is neogen, miocene, early miocene. This is when the Valencia trough moved. Those are your data from the outer Pyrenees study, and corresponds very well with some of our silicon fibers with the back-to-back mineralizations here. So it's just preliminary data, but it tells us about a Pyrenean story also involving Sardinia, which is quite cool, isn't it? Very last, which may be of interest also for those of you dealing with the volcanism of the area. It could be Spain, right? It could be the Garrocha, right? And it's in the middle of the island, and there is some north-south faults and east-west faults inherited by the possibly by the Variscan story in here, and in between of this valley there is a volcanic field, the Longdon volcanic field, which is Pleistocene, latest Pleistocene to middle Pleistocene. Composition is very primitive, so these magmas didn't differentiate much. We're doing that in collaboration with Sapienza, the University of Rome, and you see there is a very clear north-south path, but using also east-west structures. Once again, this east-west force guiding the story of the cross of Europe in this area, at least with this orientation. And well, some of those were dated in the 80s, but don't know if we can rely much on these ages. This volcano, according to the ages made in the 80s, is about 600,000 years old. Doesn't look like that, right? So who knows? And we're trying to redate everything. And there were already, this was a study of volcanic tectonics made to try to see the correspondences of these ligaments with the vents in here, north-south and east-west structures. And we had another students who tried to see the cumulative paths that had this cycle, and then this cycle, this is million years, and this is the volume. And then it depends on the age you have on these eruptions. It's important for the risk. Of course, this is an area that is a bit far away from the Einstein Telescope, but still it's in the same region. So we wanted to know about this risk because it all depends on the ages concerning this volcanic field. At least it all depends on the ages you got from some volcanoes. For example, there is a vent who had at the same time the cone and 100,000 years, plus or minus almost the half of it. And the lava flow, which was possibly made yesterday, as you can see, 140,000 plus or minus 140,000 years. So what's the age? A million years ago or yesterday? You see, and so this changes much because it's the largest as a volume, you see. And so was it at the end of the story yesterday, or was it at the beginning of the story of this cycle? This changes much. And so for the moment we are testing that, and the ages are about to come during winter time. And this is done, yes, with Rome, but once again also with Paris. So it would be very nice to learn from your volcanic field of La Garrotxa, to know better also this, because it's all related to the extinction, to the reactivation of faults in the crust in this area. So we are working on the results for the moment that we got from the private company on the Einstein Telescope. There is much. Any contribution would be accepted and welcome, because there will be very much to know about this part of Sardinia, and it's very good because the fact that Spain is also supporting this project, so it would be very nice having a collaboration. Just to sum up, today we've been talking a lot of Variscan, but actually what's the heritage of the Variscan, the late Variscan story into the present day working of the European crust, and that's done by reactivation. So the Einstein Telescope is a challenge. It's a challenge to everybody, and it's an opportunity for our geological community to know better the basement, but as you can see, also about the later evolution during the formation of the Tethyan Ocean and the Mediterranean evolution, which is still ongoing. So open to collaboration, and muchas gracias.
Many thanks, Luca. So we're time for question. I will ask you to use the microphone for question, not to speak loudly, but for the people who are online and who will follow this on the YouTube registration. So any question? Of course.
Yeah. Thanks for the talk, very interesting. My question is related about faults. Have you tried to restore their orientation with respect to the original position of Sardinia before the opening of the Ligurio Provençal Basin?
No, not yet. I didn't try. For the moment, I'm just keeping the orientation, the original orientation, as it was mostly an in-block movement. So we are just using these orientations to compare within Sardinia, within northern Sardinia, actually.
Okay, because maybe I think that these faults, maybe if you restore them, they are the continuation of these faults that we have in the Catalan coast. And it's something to explore.
Yes. So the north-south then it would be northeast-southwest, right?
Yeah.
Like the one that you have
Here is of the Catalan coastal ranges and the Valles and Penedès Free.
Yes.
And the other ones maybe are related to these faults controlling volcanism in La Garrocha.
Excellent.
It's something to explore.
Yes, we shall do it. Very good idea.
Thank you, David. More question? Yeah, I do have a couple of curiosity. The first is before drilling, don't you have some data for geophysics to have an idea of what's it down there?
Yeah, it's engineers choosing this more than geologists, and they say it was faster doing that this way.
Drilling.
Before drilling, drilling, baby drill.
Okay. And then last thing, you're talking about late Variscan, but what about the new datation, the new dating you did on the ground, right? It's a little bit older to be a real late Variscan in it.
Yes, but I went faster on that slide, but actually it was I was trying to show.
Yes,
yes, there are different populations.
For
those are the different intrusions. So basically, this is the north intrusion belonging to the big batholite, and it's coalescent with this other intrusion, the gray one, and ET45. This orange is the only actually Pluton which is isolated from the batholite, which is the old one. But also the others, as you can see, contain older zircons within the structure. So most likely it's a multi-stage evolution. And the isolated one it's smaller by definition because it's isolated. And all the rest, the big batholite, it's really multi-stage. It's coalescent and it formed multiple events through time. Then, of course, it needs to be studied more from experts in granites. But this,
yeah, but
it's open.
Very interesting data, I think.
And it's the first for the area, never made so far.
Okay, great. More question? Okay. Oh, yes, it's
Very briefly, thank you for the talk. These new H's that are you producing for the Pleistocene volcanism, I guess it will be argon dates. No?
Yes, no more potassium.
Because more accurate picture.
Yep.
okay. Thank you, Luis. Thank you, Luca, for the very nice presentation. If we don't have any more questions, I think we can stop here. And thank you for participating. Bye bye.